All righty. Well, good afternoon and welcome to this Explore Lincoln Laboratories facility session. My name is David Lee, and if you've joined us for any of our previous part of these series, this series essentially entails taking a look at some of the wonderful offerings that MIT Lincoln Laboratory has in terms of testing and just capabilities that they can run within MIT Lincoln Lab. Today's session, we're going to talk a little bit about the RF Systems Test Facility for rapid prototyping, and that is led by Dr. Alan Fenn. Dr. Fenn, I'm just going to give you a little bit of background. My name again is David Lee. I am the Northeast Regional Coordinator for the Federal Laboratory Consortium, and our region represents all federal labs from New Jersey through Maine and Puerto Rico. A little bit about Dr. Fenn. Dr. Alan Fenn received his Bachelor of Science degree from the University of Illinois, Chicago, and his master's and PhD degrees from the Ohio State University, all in electrical engineering. Dr. Fenn is the senior staff member at the RF Technology Group at MIT Lincoln Laboratory. He received the Life Fellow of the IEEE for his contributions to the theory and practice of adaptive phased array antennas. Dr. Fenn received the 2016 IEEE Aerospace Conference M. Charles Fogg Best Paper Award, the IEEE Antennas and Propagation Society's 1990 H.A. Wheeler Applications Prize Paper Award, and the IEEE-URSI sponsored 1994 International Symposium on Antennas Award. He served as the Technical Program Chair for the 2019 IEEE International Symposium on Phased Array Systems and Technology, and he was the Technical Program Chair for the 2019 IEEE International Symposium on Antennas and Propagation. We are fortunate here today to have Dr. Fenn speak to the capabilities that the RF Systems Test Facility has. If you have questions throughout Dr. Fenn's presentation, please feel free to leverage the questions box in the chat. Again, if you have questions, put them into the questions box in the chat, and I will let him know that you have questions for him. We'll also have a time, hopefully, if there is time left, we will have time at the end of this session to just have Dr. Fenn answer any last-minute questions or any additional questions that you may have to the questions that he's going to answer throughout the presentation. With that, Dr. Fenn, take it away.
Thank you, David. So again, I'm Alan Fenn, Senior Staff in the RF Technology Group at MIT Lincoln Laboratory, and I'll be describing the RF Systems Test Facility for Rapid Prototyping. As a reminder, Lincoln Laboratory is a federally funded research and development center. We collaborate with all organizations within the government, industry as needed. All right, here's an outline of the talk. After a brief introduction and background, I'll give you an overview of the RF Systems Test Facility. We have 6 anechoic chambers for doing RF testing. We have a low frequency tapered chamber, a millimeter wave chamber to go up to 100 gigahertz, a very general purpose system test chamber where we can do all sorts of measurements, compact range where we do radar cross-section measurements, as well as antenna measurements. We have a small near field scanner facility where we test small phased array antenna panels that end up being tested in our large near field scanner chamber. And then I'll summarize. So the laboratory operates a number of radio frequency anechoic chambers where we measure antennas, communication systems, radar systems. We're located on Hanscom Air Force Base in Massachusetts. And the beauty of the facility is we're located with the Lincoln Laboratory Flight Test Facility. So as we're developing flight test systems, we can build and test them at the RF System Test Facility and then basically wheel it across the hangar to the other side where the aircraft are and integrate onto the aircraft. If you're a new user, or if you want to visit our facility, you would come through the Hanscom Air Force Base Visitor Center. We would meet you there, escort you over to our facility. It's a short distance away, and we're about a little less than half a mile from the Lincoln Laboratory main campus. So a little bit of background for antenna and electromagnetic systems development. We need to do a number of measurements of important parameters for antennas. We want to measure the radiation pattern shape and gain, input impedance, all the usual parameters, mutual coupling if it's a phased array. Some systems have to operate at high altitude, so we have to test the high power handling capability. Many systems that go on aircraft or ground vehicles or ships or satellites, we have to deal with electromagnetic compatibility, electromagnetic interference, sometimes referred to as co-site interference. We do lots of measurements to verify that various systems won't interfere with each other. We often do radar cross-section measurements of scale model targets. And typically we'll do indoor anechoic chamber measurements wherever possible. Of course, in the end, we need to do field testing. So I'm showing a number of photographs, some of our chambers. And just to give you a sense for what we do, we might develop a particular phased array antenna panel. First, we do simulations, then we do fabrication, we test it in the chamber. So we test one panel, and eventually it might get a number of these panels on a large aircraft. Or we might measure a radar cross-section of a missile, showing here. And at our flight test facility, we have a number of aircraft where we can integrate antennas right on the aircraft and then fly them right out of Hanscom Air Force Base. All right, so let me go through an overview of the facility. And so we have 6 anechoic chambers, a rapid prototyping machine shop, an RF lab, a system integration lab, and we have a number of mobile test vans. So we have quite a bit of capability, fairly unique arrangement where we can develop systems on one side of the hangar and then just basically in a short period of time get the antennas mounted on aircraft for flight systems. So just looking through here, we have a number of small chambers. We have a small millimeter wave chamber, low frequency tapered chamber, a small near field scanner for developing small phased array antenna panels that go into a large near field chamber, compact range where we do radar cross-section measurements, antenna measurements, general purpose system test chamber, which is connected to a system integration lab. And so it's a very convenient way of developing RF systems. Now, if you are considering being a user of our facility, which is the purpose of this presentation, we have to consider the following. So, are you going to be doing antenna measurements? Do you want to do EMC, EMI measurements, radar cross-section measurements? We can do all that. All of the chambers are electromagnetically shielded. Basically, they're Faraday cages, metal boxes with fire retardant microwave absorber on the inside of the chambers to prevent any reflections. We can do far field and near field measurements as needed. In order to select the right chamber, depends on the size of the system and the frequency band and type of measurement. Systems would be under remote controlled multi-axis positioning, so you can see different angles of arrival, things like that. We can rotate the polarization to check out linear polarization or circular polarization in systems. The larger chambers have overhead cranes and movable carts. All the chambers are temperature and humidity controlled with lighting, RF and power cable access. We supply instrumentation such as network analyzers, spectrum analyzers, multiplexers, multi-channel switches. We have a large fabrication and staging area with some temporary storage of equipment. As far as security, we offer physical and electromagnetic security. Pretty much can do measurements at any security level. Everybody's, of course, concerned about cost and schedule. We prioritize every day. The most important projects get the immediate attention. In terms of background, we've been up and running for about 20 years, a little over 20 years, with initial operating capability in the 2003-2004 timeframe where we had 4 anechoic chambers online. And these were documented in a series of papers at the Antenna Measurement Techniques Association meeting in 2004. We added a small near-field scanner in 2011 and a large near-field scanner chamber in 2016. These are documented in the bottom 3 publications. You can read about them. In terms of frequency coverage, the chambers operate from roughly a few hundred megahertz up to 100 gigahertz, but really depends on the type of measurement. We can go lower in frequencies, we can go higher in frequencies. The compact range can handle for antennas something like 400 megahertz UHF up to 100 gigahertz W band. And in the same chamber for radar cross-section measurements, typically we would do 800 megahertz up to 100 gigahertz with objects the size of about 12 feet maximum, something like that. So we have quite a bit of capability depending on your needs and in terms of schedule as well. So we can handle many different frequencies, many different types of projects. So in terms of rapid prototyping at Lincoln Laboratory, we'll start out by doing simulations and then develop components, component characterization, put it into a system, check out the whole system, and then do field measurements, things like that. So we have a rapid prototyping machine shop, RF labs, a large system integration lab, typically where we could install racks of equipment, say radar transmitters, radar receivers, and that gets tied into the system test chamber, was right next door to it. So we have a small near field scanner, 2 utility chambers. Here's the compact range. And I'll be going through each of these in a little more detail. So at Lincoln Laboratory at the RF System Test Facility, our main goal is rapid prototyping, get systems out in the field quickly. And if they check out, then we work with industry to make technology transfer, additional systems. And again, we try to accommodate a wide range of projects, antennas, radar problems, communications, electromagnetic interference, things like that. So just looking at some of the different things we work on. At Lincoln Laboratory, we develop low-cost phased array panel technology. So we might start out with a single panel in our small near-field scanner. Once we develop the design of a single panel, we might install it in a large S-band phased array and check it out in our large near-field scanner facility. We'll do full radar system checkout before we mount antennas on aircraft. We will suspend unmanned aircraft from the ceiling in our system test chamber to evaluate the UAV. We can drive vehicles into our system test chamber. I'll go into more detail on this in a little while. And various types of large phased array antennas can be tested in our compact range. We can handle very large projects. Here we're showing the rapid prototyping shop. We've developed many different antennas over the last 20 years. We have them on display here if you come visit us. And we'll put together a large team from various groups at Lincoln Laboratory and even outside industry sometimes to build, say, a rapid prototype array that's quite large. So we're used to dealing with quick development systems that get them out to support the troops, things like that. We work on all types of radar systems. Here's an example of a ground penetrating radar system that was developed at the RF System Test Facility inside the hangar. So we fabricated a large phased array antenna, mounted it on a vehicle outside the facility in this grassy area near the parking lot. And after we were satisfied with the performance on a surrogate vehicle, the ground penetrating radar was mounted on the final up armored vehicle, which was deployed to support the troops. That's just to give you an idea of the kinds of things we do at the RF System Test Facility. All right, so let's go through some of the chambers, and if you have a particular system in mind, this information may be helpful in deciding which chamber would be appropriate. So in our low frequency tapered chamber, which goes down to around 225 megahertz and up to 18 gigahertz, we have a dual polarized feed at the conical tip region, and then 28 feet away we can put in a test object, test antenna, rotate it, and this was designed in collaboration with the Ohio State University. A fairly unique system that operates continuously over a wide frequency range with a single feed. Some tapered chambers require that you have to remove the feed and put in a different feed depending on which band you're on. So this is a wideband tapered chamber. Here's an example of a measurement in the taper chamber. 3D printed antennas are becoming more popular. This was a 3D printed phased array that we worked on, simulated it. This was measured as we rotated the antenna at L-band 1.24 gigahertz. And we have showing good agreement between the measurements and simulations of one of these circular patch antennas in our tapered chamber. And that was published in the 2016 Phased Array Symposium. All right, so that was the tapered chamber. Let's move on to the millimeter wave chamber. And that's shown here, where we would test small horn antennas or maybe a small dish antenna. We have a range distance of 22 feet, operating from 4 gigahertz to 100 gigahertz. It's a fairly standard rectangular chamber. Some of the absorber is painted blue, which helps with the visibility in the chamber. Of course, at millimeter wave frequencies, typically you would use an unpainted absorber to minimize scattering from the paint, so you can actually see the black carbon material. We have a shielded source. Again, this is a shielded room. It's a metal box with radar absorbing material all over the floor, ceiling, and walls. That's the millimeter wave chamber. Let's move on to the system test chamber. It's a very general purpose chamber. And we can do far field measurements. We can do spherical near field measurements. In the case of a phased array, we can focus the array in the near field. We can put multiple sources in the chamber. We can have jamming. We can have simulated targets. It's a large chamber, about 40 feet by 60 feet. Can operate from 150 megahertz up to about 20 gigahertz. Maximum range distance is around 10 meters. And we can handle with the overhead crane objects up to about 2,000 pounds. There are 12-foot access doors, so we can drive vehicles into the chamber. The photograph shown here is looking in the inside of the system test chamber with an X-band phased array, which we'll talk a little bit more about. All right, so in the system test chamber, I mentioned its general purpose. We can reconfigure the chamber. So here's this X-band phased array radar system that eventually ended up on an aircraft. And we spent several months checking out real-time radar system software to handle adaptive nulling, to suppress jammers, detect targets. These are the things you want to do before you go on an aircraft, which is extremely expensive once you're integrated on the aircraft. Same thing with ground vehicles. We can drive a Humvee into the chamber. We can drive all kinds of vans or whatever kind of vehicle you want. We can turn the vehicle on and pump the exhaust out through the pipe penetration tubes outside the facility. Typically, you'll have maybe a sensitive receiver system and you don't want to interfere with it when you turn on the vehicle. So, we could do real live measurements during, practical receive systems, things like that, where we can have radiating sources inside the chamber and then receive antennas and receivers integrated with the vehicle. We do ultra wideband antenna testing. Here's this high power radar test where we put the transmitting antenna inside of a bell jar with a vacuum pump. We'll pump down the air pressure inside to simulate being, say, at like 30,000 feet over the ground. Turn on, say, a kilowatt of power, make sure the antenna is not arcing or sparking or a corona, things like that. So just checking things out before you go in flight. We've done satellite antenna testing. Here's this airborne system I'll talk about in just a moment. We do radome panel measurements where you'll suspend a large, say, 8-foot panel from the overhead crane, have 2 horn antennas, measure a baseline measurement, and then drop the panel down between the horns and measure the insertion loss at a particular frequency or frequency range. Here's this UAV under test in the system test chamber. Here we had a simultaneous transmit and receive system where we wanted to have high isolation between a transmitting antenna on the tail and a phased array antenna on the belly of the aircraft. We were able to measure very low signals, a high amount of isolation, 50 dB down. You can't do this except if you're in an anechoic chamber or if you're in flight. So the the value of having an indoor test in an anechoic chamber is you can do these types of measurements before you start flying. All right, moving on to the compact range system, where we do lots of different types of measurements. Antenna measurements, phased array measurements, reflector antenna measurements, radar cross-section measurements. So this chamber was designed in collaboration with Ohio State University, and the reflector that's shown here was provided by MI Technologies. And so the way this works, this is called a compact range because we're simulating far field conditions in a compact geometry. So the way that works, we have a feed system, a series of horn antennas that will shine spherical waves onto a parabolic mirror. When the waves bounce off of the mirror, they look like flat wave fronts, plane waves that come from many miles away, thousands of miles away. So we can do indoor measurements under far field conditions over a frequency range from 400 megahertz to 100 gigahertz with a quiet zone, roughly 12 feet by 12 feet by 12 feet, a cube, almost 4 meters. In some cases, we can handle 2,000-pound targets. Here we're showing a missile mounted on a foam column. In this drawing here, we've got a phased array with beams where we rotate the antenna and measure the main beam and side lobes. There's a gantry crane where the staff and the object can ride into the chamber on these railroad tracks. We have specially shaped absorber, shaped as so-called Chebyshev to break up any waves that might scatter from the walls. And so it's a 20-foot by 20-foot rolled edge reflector antenna with a 10-foot parabolic shape in the center, and then the edges are blended away with a smooth surface to avoid edge diffraction. And so here's an antenna panel under test, which I showed earlier. This one ended up being mounted on an aircraft. So it's a fairly large facility. We use it heavily all year round. Here's a little more detail on a ultra-wideband UHF array under test. Here it's mounted on a foam column. We can rotate the lower azimuth positioner and measure the radiation pattern over a very wide band. Here we can see the feed horn is mounted at the focal point of this parabolic shaped reflector. Again, we shine a spherical wave onto the parabolic mirror and it bounces off as a plane wave. So we're actually testing the antenna as if the source was many miles away. This is basically a 44,000-pound antenna structure with a composite surface, silver conducting paint on it, and then a white latex paint over it. And this has been up and running for about 20 years. Here we're showing the low radar cross-section ogive, which is used primarily for RCS measurements, but also for antenna measurements. So when the plane wave is illuminating the target, it also illuminates this metal pylon, but it's got a sharp knife edge. It's tilted down to avoid any scattering up into the target region. So sometimes we'll use this low radar cross-section ogive, or in the same photograph, you can see one of these specially shaped foam columns. So depending on the project, we might use the low RCS ogive or a foam column for either antenna or radar cross-section measurements. And we test all different types of systems, different types of antennas, ground vehicles, ships, aircraft. Here's an example where we're testing an inflatable antenna that would come out of a CubeSat, a 2.4 meter inflatable reflector antenna, which was tested at X-band. And so just to give you a sense for the different types of things we work on in our system test facility. All right, moving on now to our small near field scanner, where we test typically small phased array antenna panels. So over the last 10 or more years, Lincoln Laboratory has been developing low-cost phased array panel technology. And here we're showing a small S-band phased array panel under test. We start out with a single panel. Once we establish that the panel is working properly, we'll put together 2 panels. So we have a 5-foot by 5-foot near field scanner. It's a probe. It will probe the near field of the antenna. That's a Near Field Systems NSI system. So there's a little waveguide probe that'll scan the near field. The data is collected with a network analyzer operating from 1 gigahertz up to around 26 gigahertz. And we can do higher frequencies as well, depending on exactly what the project is. So it's a planar scanner. The antenna is fixed. We also have a cylindrical scanner where the antenna can be rotated in azimuth. The software that we have includes holographic projection capability for array diagnostics. So when you're developing a phased array, the panels initially might not be calibrated. And so here we're showing the phase before and after calibration. So here we're showing 2 panels, and on the left panel shows a different phase. And once we calibrate the transmit receive modules, both panels are in phase. However, we can see that there are some failures of the TR modules. So the importance of a near field scanner is to be able to validate and do diagnostics on phased array antennas, and then replace any modules that need to be replaced, things like that. So then moving on now to our large near field scanner chamber. We have an 18-foot by 18-foot planar scanner, which operates from 700 megahertz to 50 gigahertz. This was provided by Orbit FR. It's a shielded anechoic chamber, 33 feet by 30 feet and 25 feet high. Has an overhead crane. We use it for phased array antenna calibration and radiation pattern testing. There's a phased array assembly area outside the chamber, and we can wheel the antenna into the chamber on these railroad tracks. Here's an example where we had an S-band phased array, which weighed about 15,000 pounds, was assembled entirely outside the chamber and then wheeled into the chamber. I'll show you a little more detail in just a moment. This system is currently out in Norman, Oklahoma, doing weather surveillance. So just again to give you a sense for the kind of work we're doing. All right, so here's the RF system test facility large near field scanner chamber during chamber measurements of this S-band phased array. So the antenna is mounted on a cart, a wheeled cart, and what we want to do is on a daily basis check out the TR modules, make sure they're working properly. So typically we'll have a transmit probe that might be fixed off to the side, and we'll just quickly run through all the TR modules, make sure they're working, and then we'll do a detailed probe scan where we'll collect the amplitude and phase data in front of each of the phased array antenna elements. In this case, we have a 5,000 element phased array. This is a very fast scanner. We'll collect dual polarized data, amplitude and phase, and then use a Fourier transform to calculate the far field based on these near field measurements. We have validated that by actually doing far field measurements on this specific antenna. So we know we're getting accurate near field measurements to far field measurements. And we'll have a gain standard mounted on the antenna so we can get the actual gain of the antenna. So that's the type of things we do at the RF System Test Facility. Let me summarize. We have a tremendous capability here. We've been up and running for the last 20 years. We now have 6 anechoic chambers, 2 near field scanners, which are very useful for phased array development, also for reflector antenna measurements. The compact range is heavily used. We do radar cross-section measurements, we do antenna measurements, and we prioritize on a daily basis. In the system test chamber, we can do a wide variety of projects, measurements. We have a low frequency tapered chamber, millimeter wave chamber. We do on-site machining in a rapid prototyping shop. We have RF labs, technicians, staff on hand, system integration lab, and we can pretty much do any type of measurement that's needed up to a certain size, typically about 12 feet, maybe a little bigger. We can handle antennas, electromagnetic interference, co-site interference, radar cross-section. You can learn about our facility by clicking on the link shown here. There's a 5-minute virtual tour you can look at. It's on YouTube. Please send us an email if you are interested in working with us. That's rfstf@ll.mit.edu. You can learn how to engage in test agreements by going to the test agreements link shown here on the bottom. And so that's what we do at the R System Test Facility. I'd be happy to answer any questions.
And Dr. Fenn, thank you so much. That was actually a very impressive. It's a very impressive facility, quite frankly. My lab has a few anechoic chambers, but not quite at the level that you guys are doing. You guys definitely do the soup to nuts, kind of can do it almost from start to finish, which is really, really tremendous. I have a couple of questions. So if someone, let's say somebody wanted, what is the general availability of the anechoic chambers and of the RS systems test facilities at MIT Lincoln Lab? How would one go about, I mean, are they usually busy? Are they, so what is the general availability of the anechoic?
Right, so we have 6 anechoic chambers. Sometimes they're all occupied, but not always. Some of the chambers are used heavily over many months. And so if there's a new project coming in, we like to know about it months ahead of time. However, there have been cases where we'll get a phone call and someone will have an important measurement that needs to be done right away. And if necessary, we'll drop everything and get that done. So we prioritize every day. The highest priority projects get the most attention, as they should. So it depends on what we're doing. Security level can be important.
Right.
So planning is really important. We will accommodate pretty much any user. We like to know as much as possible about what's needed. If we have a new user, we might do a Zoom call. We might invite the user in to see our facility. We're happy to do that. We do a lot of tours. We bring in people all the time. We like to collaborate with other organizations, and we do. And so again, in summary, we prioritize. If somebody's not in a hurry, we'll schedule it down the road, maybe a couple of weeks down the road, maybe a couple of months. So some users will contact us a year in advance, which is great. We can plan it out that way. Other questions then?
Yeah, actually, so actually, I'm gonna turn back a little bit to what you said earlier. You mentioned that there are certain projects whereby they're using it for long periods of time. They're doing maybe multiple measurements, multiple cross sections, and they have multiple requirements. Is there a maximum amount of time that one of the anechoic chambers can be scheduled? Because it sounds like there's no limit necessarily, but is there sort of a time period where you're like, oh, that's enough time?
Well, I would say the longest I know of any project in the chamber is about 9 months. Okay. And that was a case where we were doing an X-band phased array radar system that would go on one of our large aircraft. So to be absolutely certain that all the real-time radar software was operating, we spent a lot of time with integrating receivers and knowing about the A to D converters and real-time software. So I would say, yes, we have operated continuously with one project for about 9 months. That's the longest I'm aware of. But typically, we might be in a chamber for a couple of months, normally maybe a week or two. Things always take a little longer than you expect. If you're scheduling measurements, always plan on extra time. But there's really no limit, I would say, and based on priority.
So you mentioned measurements lasting for 1 to 2 weeks. So if I were going to plan that, I mean, it sounds like you do also will drop things based upon priority. So if something hot comes in that needs to be done within 24 hours, 48 hours, 1 week, it sounds like you may reprioritize and sort of do a triage system, if you will, to kind of handle the things that are of the most importance. But generally, for if you don't have a situation like that, and let's say I have a project, and I know the measurements will probably take about 1 to 2 weeks. How far in advance should I schedule it? You know, barring the last minute drop everything, all hands thing. But just for a generalized project, how much time in advance would your team need to kind of to schedule like a 1 to 2 week test period?
So probably like a month or two would be great. Like 3 to 4 months would be better. So actually, I mean, if you're building a system, you know it takes time. And if you know you're going to be using a particular measurement technique, there should be enough time to schedule it, I would say. But you know, sometimes you might have a system that's already been built, right, and for whatever reason, your chamber is not functioning, like instrumentation's not working or a positioner's not working. So you might want to rush to get a measurement done in our facility, and we would make every effort to accommodate that. And, you know, that's the way we work at this particular facility. And we're not locked in. We're not locked into any particular schedule unless it's a high priority measurement.
I mean, it sounds like based upon what you were saying about the systems integrations and the prototyping capabilities, you really can. I mean, you can handle everything from an early prototype to something that's completely built at a high TRL level that just maybe may need a few measurements and various things. Speaking of instrumentation, what kind of RF instruments are available for use with the chamber specifically? I think you may have mentioned it, but I was wondering for our audience, if you could just talk about that a little bit more.
Typically, we'll have network analyzers, spectrum analyzers, oscilloscopes, receivers, amplifiers, transmitters, arbitrary waveform generators, things like that. I will say that in our system test chamber, which is a large rectangular chamber, we have had multiple projects in the chamber at the same time. If they're doing different things, it's large enough we can spread out, maybe not necessarily operating at the same moment, but we might keep the equipment in the chamber, which saves time and staging and, you know, setup. So yeah, actually our system test chamber is probably the most busiest because we can handle so many different types of projects, and we do.
You know, for some reason, I thought that maybe having that many projects and all the additional equipment in that chamber would affect the results, but you're saying that it would not then?
Generally not, and actually, in some cases, we've done acoustic measurements. The chamber is quiet enough acoustically that in many cases we have done acoustic type measurements in our RF anechoic chamber.
Oh, okay.
You know, with speakers, microphones, things like that.
Makes sense. I'm going to ask you the indelicate question, right? Like whenever you go to a restaurant, it says seafood is market price. And, you know, everyone always hesitates to ask the waiter. I'm going to ask the indelicate question. What is the daily, weekly cost for use of one of the anechoic chambers? And I'm sure it varies, but generally, is there a ballpark figure?
Well, I can't give out a specific number, but because it highly depends on like how many personnel are needed to support the test. In some cases, a user might come in and not require much help at all and just need the chamber. However, there would be like a basic cost. And I think the best thing to do would be to contact us, and after you know, a quick meeting, we could come up with you know, a rough cost estimate and scheduling. So you know, we have formal test agreements that can be established, and we know our costs. And actually, every project at Lincoln Laboratory, we start out with a new project. We have to figure out what the cost is. We don't actually know what the daily cost is till we know what the project is. So
I think
that's my way of answering.
I mean, I guess the long and short of that would be which it totally makes sense. It depends upon the project and the sort of the intricacies of that project and complexities of that project.
That's right. Yeah, that's correct.
We have certain systems at the lab I come from whereby we do things high velocity shot testing, and it's just like boom, each shot costs a certain amount. It's like it's widgets, you know. Doesn't matter what you have in there. If we fire it, it's going to cost this amount. But it makes sense, especially if you have certain capabilities or you know, systems integrations that need to happen and certain types of analyses. That definitely makes sense. So essentially, it sounds like call us for the details depending on the project. So
yeah, and if the project has a break in time, but if the equipment stays in the chamber, then the daily rate would apply to that. If you know, if you're tying up the chamber for a period of time and maybe not actually doing an RF test, which
Mhm.
sometimes happens because equipment breaks down, and or it could be developmental type system where you're changing things.
Okay. Most of
Always plan on extra time. Yeah, you have to plan on extra time.
it's funny. I did one of these sessions for another lab, and they pretty much said the same thing with regards to the payment question. It was sort of the same thing. Was, well, it really depends on what you want us to do specifically within our facility. But and also they also said, yeah, give us a lot of lead time because these things take time to plan out, and to think about carefully.
Yeah, I mean, in terms of cost, in terms of the facility itself, you're thinking of tens of millions of dollars over 20 years. So I mean, that's where the cost would come in. You're getting a tremendous capability,
Right.
which maybe doesn't exist elsewhere, or not available.
And to your point, I think what I've noticed about Lincoln Lab is that your facilities, it's not just the equipment in and of itself, it's the expertise that using the equipment and the analysis that comes with it, and the expertise that that people are able to leverage when they engage in work with Lincoln Lab, which is really tremendous. I mean, it sounds like, just having talked to some of your colleagues in some of the other facilities, the amount of depth of technical expertise there and experience is just, I mean, you have at least 20 years. It sounds like at least possibly more than 20 years with RF, which is just tremendous.
Yeah,
So,
I mean, I've been doing these kind of measurements for over 40 years, actually.
okay.
Yeah, I joined Lincoln Laboratory over 40 years ago. So we
Oh my
had
God.
we had a separate facility in Bedford, Massachusetts, not on Hanscom, where we had outdoor ranges and indoor ranges. I actually prefer the indoor ranges because they work very well during the winter, the summer, and the heat and rain and humidity and all that. And I'd rather be indoors whenever I can, plus for security purposes as well.
Absolutely. I mean, so that's a great question. And also, number one, apologies. I did not guess 40 years. You don't look like you've been working for that long. So I'm just going to say you probably started out of high school or elementary school, something like that. So good for you. That's
Oh,
tremendous. But
yeah, maybe working hard keeps you young. I don't know. We'll
I
see.
think so, as long as you enjoy it. I
Yeah, I
classified
do.
information, which is you hit on a great point, which is really interesting about classified stuff. So what kind of classified, let's say I have results that I really are classified, that, we're working on systems that are classified, and the results, do you guys have, what is your system for handling that? How do we talk about that? Who are they
We
talking
can,
to?
yeah, we can talk about that. In our compact range, it can be locked up as a safe, as a SCIF.
Okay.
So we can work at any level in our compact range. The other chambers, we could pretty much work at any level with guards,
Okay.
and working it out with the security of each organization until
Okay.
everybody's satisfied. And we have done that.
That is really, for some, because I know anechoic chambers, some of the measurements are, especially depending on the type of test and what you're trying to test for what purposes, the results can be classified. So I know that that's certainly a big concern out of a lot of people who may be watching this, and
Yeah.
so that's thank you for answering that. That's really good that you have that experience and can provide that level of security as well, that level as well as that level of expertise to do that. No,
Yeah, it's very well. We're very secure. I mean, it's hard enough to get on a Hanscom Air Force Base to begin with, and then we're in a locked hangar, and then the chamber's locked, and yeah, it's very, very, very secure.
That's
Very
good
few people have access to the building, period.
So speaking of access, where would you say the bulk of your customers come from? I mean, I'm assuming a great majority of them are DoD or DoD contractors. Are there any other groups that you would say, any big population groups that you guys cater to?
So we do a lot of work for the Air Force, the Navy, the Army. I mean, so it's mostly government
Okay.
funded. Occasionally we'll work with industry,
Okay.
but mostly it's high priority, rapid type government projects, and typically large teams. People doing all different types of things, integrating systems together to go on aircraft or ground vehicles or whatever.
Okay. Okay. Interesting.
I mean, I can give you an example. So
Okay.
in some cases, the government will bring in a certain aircraft, and they'll have certain requirements for the RF system. So we'll work on the RF system on one side of the hangar, and within a month or so, we can be integrated onto an aircraft, something like that. That's how quickly we can work.
And that's wonderful. I mean, I'm just thinking, so when you say, like, let's say aircraft, like an Air Force, let's say, would it be the contractors who are working under an Air Force contract or something like that?
Yeah,
or is it
could be. It could be. Yeah, it definitely could be.
Okay. Do you guys ever work with universities as well?
We do. Yeah,
Okay.
we had university out a couple months ago.
Okay.
We work on proposals together, so we might collect data to go into a proposal, things like that.
Very good. No, very interesting. Again, I'm just asking. I'm just kind of wondering about our audience who's out there, and I know we have some attendees, and this will be recorded for future posterity. They're probably asking the same questions. What kind of groups do you have experience with? And
Well, last week we had high school students coming in for a tour. They come to Lincoln Laboratory and build radar systems, learn about radar. They spent a couple weeks, and so we had 30 high school students in last week. So we see everybody. We have government officials coming in. We have all kinds of sponsors coming in, and every week pretty much. It's a very interesting facility. Every day is a little different, and that's why I like coming into work. It's never the same thing. Every day is different.
That's awesome. I mean, what kind of high school builds radars? That's a pretty advanced high school.
There's some pretty smart students out there. They're learning a lot. It's competitive. They offer this course every year, every summer for 2 weeks. Students come to the laboratory and learn about radar. Build a little laptop radar, test it out, and then take a tour of our system test facility. That's been going on for many years, actually.
That is wonderful, and that is really impressive. I'm assuming that the high school students didn't have to pay additional money or great sums of money to go to work with the RF test facility.
No, they don't have to do that. No.
That's wonderful. I'm not seeing any questions from our audience. I think your briefing was very, very complete, and I love the pictures, love everything about it. And you have all the information for our audience. As you can see, there are links there. There are links in the chat provided by Stephanie. If you want to engage with the RF test facility at MIT Lincoln Lab, in the absence of any questions, is there anything else that you would like to add, Dr. Fenn, regarding this? I mean, the capabilities are impressive. I mean, the way that you guys can go from pretty much soup to nuts, and the depth of experience you guys have I have not seen it in other labs, quite frankly, so I'm impressed.
Yeah, so I mean, the RF system test facility exists to support projects, important projects, both within the Lincoln Laboratory and, external organizations. So we're here, and we would like to hear from you, and we're ready to do testing.
Outstanding.
Integration of systems, whatever is needed. That's what we do.
I apologize. We actually have a couple of questions.
Okay, good.
You offer partnership with access to the facilities using CRADAs. Are these startup-friendly CRADAs where a startup can offer in-kind contributions with the RF facility?
We do non-disclosure agreements, and we can also, in some cases, collaborate. We have to be careful because we can't compete with industry. So it depends on what the project is, but yes, I mean, we can certainly work with startups. We have done that.
Okay.
Some of our technology ends up going into a startup. I mentioned the ground penetrating radar, which originally had a military application, but then it transitioned to a civilian application in a startup company. So, I mean, that is something we would be, we can get involved in, and we do.
Weird question. The civilian company that used it, what did they use the technology for, if you don't mind me asking?
So imagine driving down the highway in the middle of the night in a snowstorm and you can't see the road. So they would have a ground penetrating radar that previously had measured the characteristics of the pavement beneath the vehicle over thousands of miles or in cities or wherever. And by doing actually in real time, knowing exactly where you are relative to the rocks and pebbles and voids under the ground, it will keep you right on the highway and not run off the road in the middle of the night, in the dark, in a snowstorm or a heavy rainstorm. So there are efforts to make a ground penetrating radar on every vehicle sometime in the future. You know, I don't know when, but that's where you might use a ground penetrating radar.
Okay.
And if you can imagine the vehicle driving by itself, you know, there are self-driving cars now, so maybe someday you'll be using a ground penetrating radar in addition to the cameras and whatever else radars not looking in the ground, but you know, that's what the future holds, maybe.
I would not be surprised, given the updates of software and sensor technology that are being added to electric vehicles regularly.
Yeah.
That really does not surprise me, would not surprise me at all. Going a couple steps back to earlier when we talked about security clearance, is there a security clearance, a basic security clearance required to access the facility? It sounds like it can be made very, very secure, but can it also be made accessible to the public?
If the visit is unclassified, so for example, the high school students, of course, did not have security clearances. So you can come in. We don't allow foreign nationals into the facility, but any U.S. civilian, U.S. citizen can come into the facility with an invitation and an escort. And, you know, we can do unclassified measurements, of course.
Okay.
So, you know, we're pretty open to collaborations.
Okay. Okay. Very good. That makes sense. It's sort of the same at our laboratory as well. We can kind of clean up everything and just make it at a very distribution A, whatever, very basic level. Again, going back to the indelicate question about fees, and I do recognize that, and that a lot of labs, of course, it's depending on the nature of the project. That's going to determine the cost of the project. But are there, for more, let's say hypothetically, someone said, hey, I just need to use an anechoic chambers, one of the chambers, with this very basic measurement. Are there is there an hourly fee for equipment use or facility use? And that's being asked from our audience.
I would say it's a daily fee, because it's pretty hard to set up immediately and get your data in, you know, like in an hour or two. I mean, it's probably not possible. So it'd be like a daily rate. You'd have to do it that way. Plus, things always take longer than you expect.
Correct. And
so I don't think it would ever be hourly.
Okay. Okay.
It's unlikely.
Okay, which makes sense, because you know, people think that's going to take a certain amount of time or a certain amount of effort, and sometimes usually people tend to, in my experience, people tend to underestimate what it takes to get appropriately set up and get the equipment running appropriately.
Yeah, we're always optimistic that things will go extremely well, but with measurements, everything has to be perfect, and it takes a little time to get things perfect.
I'd imagine.
And before we release any data, we always make sure that the data is accurate. I mean, it's quite possible to take data that's not accurate, but we check things. So we'll work with the user to make sure that they're getting accurate data.
I've got to ask Dr. Fenn, as part of, you know, you have 40 years of experience. How much, if you had to add up all the years of experience on your core team, how much would you say that is? How many people would you say that is? And how many years of experience?
Probably 200-300 years.
Okay. Okay. So
yeah, most of the people have been there a long time, have a lot of experience. We do have some new people, but they get up to speed very quickly.
That's and honestly, I think that's what, you know, again, from having spoken with and presented for the MIT Lincoln Laboratory facilities, that seems to be the thing. It's not just the equipment, it's the expertise and the experience at doing the measurements, at running the equipment, at working different projects that I think a lot of our customers can benefit from. So again, ladies and gentlemen watching out there, MIT Lincoln Laboratory RF Systems Test Facility is here to work with you and has that level of expertise to help you get past whatever things you need to do with regards to RF systems testing and integration and prototyping. Dr. Fenn, I think that's our last question from the audience. Is there any last comments or words, sir?
No, I appreciate the opportunity to speak, and I thank you, David.
Thank you, sir. Ladies and gentlemen, this concludes our facilities in-depth tour of the RF Systems Test Facility. If you have any questions or concerns, feel free to reuse these links There are some stuff on YouTube, there are emails, and there's some links here available that you can reach out, you can use to find out more or get details in terms of engaging, if you would like to engage the services of the RF Systems Test Facility. Dr. Fenn, team, thank you so much for your time.
Yeah, thank you.